Math 2415, Calculus 3, Multivariable Calculus, Chapter 10, Vectors and the Geometry of Space, Section 1, Three-Dimensional Coordinate Systems, Video 4, Distance and Midpoint Formulas. Now, at the conclusion, these are really simple because they're just as easy as they are in their two-dimensional varieties. But the bulk of this video is actually going to focus on proving the distance formula in 3 dimensions and kind of sketching out a proof for the midpoint formula in 3 dimensions, because I don't want this class to just be, let's write down some formulas and spit out some answers and say this means that in terms of physics and engineering. I'm a mathematician by trade. I only do physics and engineering as necessary to teach the math classes. So I like to focus on the more theoretical side of things from time to time, which at this point really includes proofs. And for those of you going into a more mathematical direction, i.e. math majors, you will get to classes where every exercise you do is a proof, where you claim something is true, and then you prove it using logic and based on knowledge that you already know to build new knowledge. So don't freak out too much if the proof part of this throws you off, but I want you to try to follow as much of it as you can. All right, so let's get right down to it, starting with the distance formulas. Distance formulas. Now, you should already know the 1 and 2 dimensions, and well, you just saw pieces of them there. I do want to point out that the word processor in Zoom, which is what I use to record these videos, does not allow me to type superscripts such as powers or subscripts like x1, y1. So when I'm typing these, I will often just type something like x1, meaning what you would normally see as something like x1 with a subscript, and same thing with the y1 here. So if you ever see a letter followed by a number, it's usually my lazier way to type a subscripted number, so I don't have to type more text boxes than necessary, change font size and reposition them. You'll see some of the superscripts and subscripts that I'm talking about here in a moment. But in 2 dimensions, the distance from x1 to x1 comma y1 to x2 comma y2 is simply the square root of the sum of the squares of the differences of the corresponding coordinates. Okay, let that sink in as I say it again, and this time I'll slow down and highlight some things. The distance between 2 points in 2 dimensions is the square root of the sum of the squares of the differences of the corresponding coordinates. So the square root of x1 minus x2 minus x1 squared plus y2 minus y1 squared. The order of the subtraction is irrelevant because you're going to square it anyway. If you turn a subtraction problem around, you get the opposite answer. Like if I subtract and get 5 and turn it around, I get -5, but I'm going to square it anyway. Both will come out the same, in that case, 25. So what do you think the distance formula in 3 dimensions looks like, where you have a third coordinate to account for? If you were thinking it looks the exact same, except it has a third addend under the square root, you would be correct. Because the only difference is you have to add the square of the difference of the z coordinates under the square root. So the distance is the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. So pretty easy to go from 2 to 3 dimensions. We're actually going to prove this formula. Now, how would we prove this? Well, we're going to prove it on the assumption that we can do things in 2 dimensions, and then we'll take it up to 3 dimensions. This is a very common strategy for dealing with higher dimension spaces, both in math and physics and engineering, is that you try to ask yourself, do I know how to do this in a lower dimension? Do it in the lower dimension, and then see if you can bring it up to the dimension that you want. So we're going to prove that this is the 3-dimensional distance formula by boiling it down to two-dimensional things that we know about. So how are we going to do that? Well, here's where it gets a little bit more mathy. Let's see if you can follow along. We're going to consider the points A, coordinates x1, y1, z1, and B, coordinates x2, y2, and z2. And their projections, A prime, whose coordinates are x1, y1, 0. So we're projecting into the xy plane. And B prime, whose coordinates are x2, y2, 0. So 2 points A and B and their projections in the XY plane. And I kind of already have a picture drawn here. You see A and B floating around in the sky. Here's A, here's B, and then their projections down here into the XY plane. So keep in mind that the 2 points on the bottom are sitting in the XY plane. Now, we're going to bring in a fifth point here, and we're going to call it point C. And the coordinates of C are going to be almost the same as the coordinates of B and its projection. It's going to have the same the X, the same Y. So X2, Y2. But we're going to give it the same Z coordinate as A. So what does that mean about the point C? Well, first off, because it has the same X and Y coordinates as both B and B prime, it's going to lie in the line segment B prime, and that line segment is parallel. It's parallel to the Z-axis, but also because points A and C have the same Z coordinate, Z1, then they both lie on the plane Z equals Z1. So they both lie on the same plane that is parallel to the XY plane. So those are going to be key aspects. Again, point C is on the segment containing B and B prime, and AC, both A and C in the segment connecting them, lie on a plane that is parallel to the XY plane. So how's this going to help us? Well, we're going to do the distance formula down on A prime, B prime, because they're essentially in a two-dimensional place right now in the XY plane. Also, I'm going to bring in a new notation, and this is fairly common in upper level math. I'm going to represent distance as a function. Now, unless you've had this class before, you probably haven't seen a function that has more than one input. And when I say function, I mean something like f of x. But normally you only have one input. We're going to see functions with multiple inputs in this course. So I want to go ahead and introduce you to the notation. The notation is the same as function notation in general. You got the name of the function, which is generically an f. I'm using d for distance. And then you have the list of the inputs going into the function, which up until this course has always been a single input. Well, there's nothing that says a function can't have more than one input. So I'm going to let d of x comma y be a function that says, I'm going to tell you the distance from point X to point Y. So keep that in mind. Little d now means distance between the 2 points that follows. Now, and I kind of already mentioned this, but since A prime and B prime can be viewed as 2 points in the two-dimensional XY plane, so let's go back over here. These 2 points down here live in a plane, and honestly, any 2 points always have a plane that they live in. I would argue that there's an infinite number of planes that contain the points A prime and B prime, but most importantly, they both live in the XY plane. So we're taking this down to 2 dimensions. We're taking it down to the XY plane. But since A prime and B prime can be viewed as 2 points in the two-dimensional XY plane, we can use the two-dimensional distance formula to determine that their distance is basically just the distance formula, the square root of x2 minus x1 squared plus y2 minus y1 squared. Go back for a second, make sure you understand you're buying what I'm selling. Here's A prime, we can ignore the 0. And here's B prime, and we can ignore the 0. The technical word that pops into mind here is called embedding. We're embedding A prime and B prime into a two-dimensional space. That two-dimensional space is the XY plane, almost as if the z-axis never existed and we're still living in just x's and y's. So if we apply the distance formula in 2 dimensions to the 2 points that are highlighted without their z coordinates, since they're both 0, since we're living in the xy plane, then their distance is this. All right, cool. But how does that help us? Well, go back to the picture for a second. Notice that this segment, A prime, B prime, and this segment, AC, look like they ought to have the same length. Now, when you're proving something, you can't just say, well, it looks like that. You got to be a little bit more rigorous than that. So let's see if we can convince ourselves that segment A prime, B prime down here, which we just found an expression for their distance, and segment AC, let's see if we can geometrically show that those are congruent and hence have the same length, distance between the same distances. All right, since segment A prime A and B prime C are parallel, let's go back and look at that. Oops, where'd it go? A prime A is here. And these are parallel. Those two segments are parallel. Why? Well, think about it. A and A prime both have the same X and Y coordinates. The only difference is their Z coordinates. One is 0, one is Z1. And so being projections, the segment that connects them is parallel to the Z-axis. Similarly, B prime is parallel to the Z-axis, but C is on that segment, so CB prime is also parallel to the Z-axis. And if I'm parallel to this and you're parallel to that, then we're parallel to each other. All right, so since segments A prime A and B prime C are parallel, both are parallel to the Z-axis, and congruent. Oh, wait a minute. Why would these two segments, these two vertical segments, be congruent? Well, we could do the distance formula between them, but let's think about it for a second. And I'm getting a lot of highlights here, so I'm gonna have to get rid of some of them. All right, let's focus on A and A prime just for a second. Here's A prime. If we did the distance formula, oh, wait a minute, we can't use the three-dimensional distance formula. And why is my name still there? Hold on, why is my name still there? Okay, there we go. We can't do the three-dimensional distance formula on that for a second because we're proving the three-dimensional distance formula. But notice that these 2 points, the only difference in their coordinates is their Z coordinates. So A is directly above A prime, and the distance between them is the coordinate of the Z coordinate of A, Z1, since A prime is the projection. So the distance between A and A prime is, in one dimension, if you will, is Z1. What about C and B prime? Well, the way C was chosen, and let me bring back my toolbar. Where did it go? I need my toolbar. Here we go. Sorry, I made something disappear. I had to bring it back. But if we look at the coordinates for B prime, which are here, and C, which we chose, notice that they also have the same X and Y coordinates, and that C is directly above B prime, and B prime is on the XY plane, so its Z coordinate is 0. And so the distance between B prime and C is also C1. And that basically means that the two segments that are highlighted are congruent. They have the same distance between they have the same lengths. So where are we in all this? Since segments, where are we? We're right here. These two segments are parallel because they're both parallel to the Z-axis, and congruent, they both have a length of Z1. Then quadrilateral A prime A C B prime is a parallelogram. Wait, what? Getting a little bit of geometry on here. I'll tell you guys the same thing I tell my Calculus 2 students. Everything you've ever learned in math is fair game. And I know for a lot of people, geometry is a weak point. C'est la vie. This quadrilateral has the following features. These two sides, A prime A and B prime C, are parallel, both parallel to the Z-axis, and congruent. They both have a length of Z1. And there's a theorem in geometry that says in a quadrilateral, if a pair of opposite sides are simultaneously congruent and parallel, then the quadrilateral is a parallelogram. I'm not going to prove that, but the shape highlighted in yellow is a parallelogram. And one feature of a parallelogram is that opposite sides are not only parallel, but congruent. Well, guess who are opposite sides on this parallelogram? A prime, B prime, the bottom, and AC, the top. That means the bottom of this and the top of this have the same length, but the bottom of it, the length we found in pink. And so if you put it all together, that means that the distance from AC is the same as the distance from A prime to B prime. Translation, the top of the parallelogram is just as long as the bottom of it. Okay, so why do we want to do that? Because what I'm trying to do is take this thing I figured out down here in the XY plane, push it back up into the sky, because what I'm going to look at next, I'm going to highlight it. What I'm going to look at next is this triangle, which I can think of as a two-dimensional object because it's just a triangle. And And we're going to hit it with the Pythagorean theorem. But we need to make sure that the Pythagorean theorem applies, which means we need to make sure it's a right triangle. Well, in that triangle, ABC, guess where the right angle is? It's angle ACB. It's right here in this corner. So consider triangle ACB. The length of segment CB is Z2 minus Z1. So let's go back and think about that for a second. The length of the segment over here. Well, we know that the Z coordinate of C is Z1 and the Z coordinate of B is Z2. And we're basically measuring distance in one dimension now. And so the distance is just the difference in their Z coordinates. So the distance from the length of side CB is Z2 minus Z1, which we have highlighted in green. Also, we know that CB is perpendicular to the XY plane. CB, this segment here, is perpendicular to the XY plane. Now, why would that be the case? Well, because segment CB is part of segment B prime B, and we know B prime B is perpendicular to the XY plane because it's the projection. And since BC is parallel, since the top part is parallel to the entire segment because it's contained inside of it, and the entire segment is perpendicular to the XY plane, then this segment up here has to also be perpendicular to the XY plane. But the XY plane is parallel to the plane containing the segment AC. Let's digest that. The XY plane, the floor, is parallel to the plane containing, how did I phrase that in the word here? CB is perpendicular to the XY plane, so we established that this was perpendicular to the floor, and the XY plane is parallel to the plane containing segment AC. I'm going to be real nitpicky here. Is parallel to a plane containing segment AC. The reason I changed it to a plane is because there's an infinite number of planes that contain this light segment. What do I mean by that? Well, imagine I think I accidentally unplugged myself. All right, let's stop sharing for a second. Look at the spine of this book. Think of it as a line segment. Sorry, it's acting goofy. Now, that line segment belongs to every one of these pages. So as I fan this out, every one of these planes, contains the spine of the book. And it doesn't matter if I'll fan them, if they're all parallel, or if I'll open them and fan them out. But every one of these planes would contain the spine of that book. That's not really the best example. Here's another example. You ever been in a revolving door? You know, there's an axis right down the middle of it, and each of the parts of the door represents a plane. As that door revolves, each part of the door is representing a different plane, all of which contain the axis. So there's an infinite number of planes that will contain any given line. Now, why am I mentioning all this? Because there are an infinite number of planes that contain AC, but one of them is parallel to the XY plane. Why is that important? Because we're trying to establish this right angle right here. And we've established that BB prime is perpendicular to the XY plane, and the XY plane is perpendicular to a plane containing AC, which means that the segment BC is perpendicular to AC. Not sure if I said that as clearly as I wanted to, but let's wrap this up. We have a right triangle. This green thing is a right triangle. We know the length of AC, or an expression, because it's the same as the length of A prime B prime. And we know the length of BC because it was just the difference in their Z coordinates. So we should be able to hit the Pythagorean theorem to find the length of AB, which is the distance between A and B. Let's wrap this up. All right, so ACB is a right angle. We can apply the Pythagorean theorem to triangle ABC, and in terms of distances, that means the hypotenuse squared, the distance from A to B, is equal to the sum of the squares of the legs. One leg's distance being, one leg's length being the distance from A to C, the other one being the distance from C to B. Looking at the picture again, the hypotenuse squared is equal to this leg squared plus this leg squared. And now we just chase down the algebra. We had already established that the distance from A to C is the same as the distance from A prime to B prime, which was this thing in pink. So this thing is the first distance. I'll highlight it in pink so that you can keep up with it, because it says a lot going on here. All right, so there it is. And we had already established that the distance from C to B was Z1 minus Z2. It's still highlighted in that kind of green color up there. So we're going to highlight it in green here. On this part, the square on the outside cancels the square root, which is why the square root disappears here. And then tack on the third part, we have all this. So that's the square of the length of the hypotenuse. And now all we got to do to find the distance from A to B is to take the square root of both sides. And we get that. This formula can be extended to as many dimensions as you want. I thought about just doing some examples, but you're in Calculus 3. If you can't plug numbers into this formula and simplify the square root, we need to have a talk. Let's talk about the midpoint formula really quickly. Midpoint formula is just a natural extension from 2 dimensions to 3 dimensions. There's my name floating around again. I can't figure out why. Okay. In 2 dimensions, the midpoint between x1 and y1, excuse me, the midpoint between x1, y1 and x2, y2 is, I'm trying to get my highlights ready. The x-coordinate is the average of the x-coordinates, and the y-coordinate is the average of the y-coordinates. Most common mistake people do here is they do a subtraction problem. Stop. The midpoint is the average of the 2 points. Average the x's, average the y's. In 3 dimensions, it's the exact same thing. You just got to average the z's. We're not going to prove it, but if you're a math major or plan on being a math major, I'm going to tell you how you would prove it. I strongly recommend putting pencil to paper and trying to prove that this is the midpoint of the 2 points in 3 dimensions, x1, y1, z1, x2, y2, z2. I'll map out how it goes. To prove this, you would let A and B be 2 generic points, x1, y1, z1, x2, y2, z2, and let M be the alleged coordinates of the midpoint. In other words, M would be the average of the x's, comma, the average of the y's, comma, the average of the z's. To prove that one point is the midpoint of 2 others, you have to show 2 things. Number 1, you have to show the distance from one point to the midpoint is the same. So the distance from A to M and the distance from B to M are equal. But that's not sufficient, because showing that M is equidistant from A and B would simply mean that it's on this perpendicular bisector. For example, if I picked a random point up here, then its distance from A to B is going to be the same also. That's a property of the perpendicular bisector of a line segment. Any point on it is equidistance from the endpoint. So showing that the distance from A to M and the distance from M to B are equal only puts it on that perpendicular bisector. You also have to show that the distance from A to B, so the distance all the way across, is equal to the distance from A to M plus the distance from A to B. And what that does is it shows you that M is collinear with A and B, that it actually lies on the line segment. So to be the midpoint, you have to satisfy 2 criteria. Number 1, you have to be equidistant from the endpoints. And number 2, you have to be collinear to them. Notice that this proof is simply calculating some distance formula stuffs and showing that 2 equations are equal, that these 2 distances are equal, and the total distance is equal to the sum of the distance of the parts. You would have to chase down a lot of X, Y's, and Z's, but it is manageable. It is easy to do. I would strongly recommend checking it out. This one's going to be easy. This one, I'm pretty sure I know what would happen. It's actually pretty easy. So I give it a try. Impress me. You want to write it out, then drop me a message and I'll take a look at it and give you some feedback.